In this video, we're going to look at a transient response from an initial steady state condition, but we're going to consider a type 1 Dirichlet top boundary condition. We'll examine this response in two ways, looking at the head distributions through time and also the flux as a function of time across the top and bottom boundaries. Here we're considering a transition from the initial steady state, the white lines, to the final steady state, the green. The head changed at the top boundary immediately, and it has to transition from that top boundary where the head is fixed down to meet the initial steady state profile. The universe, through us, has applied a constant type 1 boundary condition, a high head at the top, and the column responds by changing the gradient within the system in response to that head. At this point in time, the column has not felt any response below this depth. It does not know that there's a transient above it. Just as for the constant flux top boundary case, we have a change in gradient with depth. That means at any location, we have more flow coming into that location from above than we have leaving from below. That means, of course, that we're going to have an increase in storage at that depth, and therefore we would have an increase in pressure with time at that depth. The result is a rightward shift of the pressure or hydraulic head profiles, and that gets muted in time, moving towards the straight steady state distribution that we would see at the final condition. So that just leaves us to think about what the flux looks like as a function of time into and out of the column for this type 2 top boundary condition. It turns out that it looks quite different. The top boundary, now rather than having a step change, has a very high gradient when we first change the constant head boundary condition. We have a very large downward flux, and then that decreases with time as that gradient at the surface decreases to the final gradient. The bottom boundary has the same shape. There is a delay, and then it slowly comes up to the final gradient. But if you notice, that actually happens much faster in this case, because that early high gradient is driving much more water into the column than the type 2 boundary condition. Just as before, steady state is defined macroscopically as the time that the inflow and outflow are equal. It also represents the time that the inflow and outflow are the same at every point in the column, and that there is no longer any change in storage with time in the column from the flow equation. And that area between the curve, even though it has a different shape, it still represents the change in storage. And because we have the same initial and final conditions, it must be exactly the same amount of storage change. The remainder of this video is set up as embedded quizzes, so again you can skip forward any time that you like. The question here is, if you impose a type 1 Dirichlet top boundary condition, what remains constant at that boundary and what changes during the transient period? The idea, of course, is that you can define one or the other condition at the boundary. Here we're defining the value of the hydraulic head, so the gradient in the hydraulic head must change with time. Thinking a bit more about that, the reason that the gradient changes with time is that the pressure just inside the column, beneath that constant head boundary, is increasing with time as storage increases. So the gradient across the boundary is decreasing. Next question, why does the type 1 constant head or defined head boundary reach steady state faster than the type 2? In this case, we are imposing a high gradient at early time, so we're driving a lot of flow into the top boundary. In fact, the minimum flow that will occur at the top boundary for the type 1 is the final steady state. In contrast, for the type 2, we set that low final flux, and it remains through all time. So essentially we're driving much more flow into the column at early time, and so it eventually fills the change in storage faster, reaching steady state faster. This was meant to be a very exciting race to the answer in class, having you raise your hand as soon as you knew the answer. What boundary condition type should be applied to represent a falling head test? Now, this is a pretty tricky one actually, and it has to do with where the boundary of the domain is being defined. In this case, if we think of our soil buddy, the top of the domain is really the top of the sand, and we can look at that falling head as the applied boundary condition. So we could do either. Probably the simplest is to think of this as a defined head. The ponded height of the water is the pressure head, and that defined head is changing with time. So it's not, in this case, a constant head boundary. It is literally a defined head boundary where we would have to define that value as a function of time as the water level fell. Now for the soil buddy, of course, we know the area of the soil buddy body, so we could also determine how much water is flowing in as a function of time, and we could equivalently define this as a type 2 boundary condition. In either case, we would have to have a value of that boundary condition that is changing in time, which is just a good illustration of this idea that a defined boundary is not a fixed or constant boundary.